So now on our third model of the atom, the first one, the Dalton solid sphere model of the atom, says, look, you got a solid sphere like a pool ball, like a marble, nothing inside it. The Thompson plum pudding model of the atom was our next one, 1897, where Thompson discovered the electron using the cathode ray tube, said that the atom consists of a sea of positive charge with a bunch of little negatively charged electrons floating around inside it. Then we fast forward to the Rutherford experiment, the gold foil experiment, where he had essentially a box of radioactive particles that released alpha particles. Those alpha particles fired at this gold foil, and then he observed where these alpha particles struck the screen. He found that most of the alpha particles did what? Most of them did? Yeah, most of them went straight through. What did that tell him? The fact that most of the alpha particles went straight through told him and his assistants that? Yep. A lot of empty space. Most of the atom is empty space. Not all of it, but most of the atom is empty space. Some of the some of the alpha particles did what? Most of them went straight through. Some of them changed direction. Some of them were deflected, not bounced back, still went through the gold foil, but some were deflected. What did that tell them? The fact that some of these positively charged particles, alpha particles, were repelled by something. That something must be small, because most of the atom is empty space, but that something must also be positively charged. The only thing that repels something that's positive, i.e. the alpha particles, is something that's positive. So the small nucleus must be positive. A few of these alpha particles did what? Yeah, a few of them bounced back, not necessarily straight back, but a few of them bounced off of the gold foil or reflected off of the gold foil. What did that tell them? What else do we know about this small positive nucleus? It's not necessarily solid. It's got to be heavy. It's got to be dense, right? Because these heavy alpha particles aren't going to reflect off of these tiny, tiny light nuclei. They've got to be fairly heavy nuclei for the alpha particles to bounce back. And then we went to the Bohr model of the atom, which was yet a further step forward from the Rutherford model of the atom. Looks essentially the same, but it acknowledges the existence of electron levels, not just electrons orbiting around in circles around the nucleus wherever they want, but they orbit around in specific levels, each of those levels characterized by a specific amount of energy. The second aspect of the Bohr model of the atom talked about stationary states. Remember that Maxwell said that electrons orbit around the nucleus, they accelerate, they should emit electromagnetic radiation, but they don't. Something's wrong here, right? They're not emitting electromagnetic radiation like they should, according to Maxwell's theory. It's as if they're not accelerating. In fact, it's as if they're not even moving, but they are. So there's a little bit of a problem here. Bohr said it's a stationary state. It's as if they're not accelerating. It's as if they're not moving. Thirdly, we talked about electron transitions. Electrons can jump to a higher level, from one level to level 5, or from level 3 to level 7, or from level 2 to level 3. How do they do that? They got to absorb energy. Usually that energy is in the form of what? Not always, but usually in the form of, electromagnetic radiation. You absorb a photon of visible light. You absorb a photon of ultraviolet or infrared, and an electron can jump to a higher level, an energy level that is that much higher, or the energy of that level that it jumped to is the amount higher than the first level, corresponding to the energy of the photon that it absorbed. Electrons can also fall to a lower level. When they fall to a lower level, what happens? They give off energy. Good. They lose energy. They give off energy. And when they give off that energy, it's always in the form of what? When they absorb it, it's usually in the form of EMR. When they give it off, it's always in the form of EMR. Good. All right, finally, this is pretty much where we left off yesterday. And this is what I photocopied for you here for you today. We talked yesterday about these two different spectra that we see down here. The top one was just a reference, right? When we had a solid that was hot, or a liquid or gas that's under high pressure, it emits a continuous spectrum. It emits white light. All the colors are together, but it looks like white light. Looks completely white. When that white light goes through a prism or diffraction grating, it splits up the white light into its component colors. It splits it up into a rainbow. This is our reference diagram, diagram number 1. Now, diagram number 2, we got something similar here. We got a hot gas, but this time this hot gas is under low pressure instead of being a solid or a hot gas under high pressure. What happens there? Well, the electrons are energized. The electrons are in higher levels, and they want to go back down to lower levels. So what do? When they go back down to lower levels, they give off EMR. But they don't give off every single color of EMR. They don't give off a continuous spectrum. It may look like white light when it's coming out, but when we put it through a prism or a diffraction grating and split it up, we can see quite clearly that it's not white light. It's not a rainbow that's formed here. It's very specific colors that are formed. Each of those colors correspond to a particular frequency of EMR that was released, that was given off when an electron made a transition. So this one would correspond to one transition, this one would correspond to a different transition, and so on and so on and so on. Finally, the last one, take away that cold gas, we have the first diagram again. But when we introduce that cold gas, all of a sudden, some of this light that was produced, this truly white light that was produced by this heated solid, liquid, or gas under high pressure, some of it gets absorbed, causing electrons in the cool gas to jump to a higher level. When they jump to that higher level, they take away some of that continuous spectrum. So now what we have, when we pass it through the prism or diffraction grating, is a continuous spectrum minus certain colors, certain frequencies that were absorbed. Make sense? We gave an example yesterday, and we saw how we could identify the composition of an unknown gas simply by comparing it against known spectra. So these would be published. We would know what these spectra were by experiments. And then when we see something that was unknown, like the light that was coming off of a distant star, then we would examine it, compare it to known spectra, and say, oh, look, we know what it is. In this case, I think it was hydrogen and sodium, I think it worked out to be, wasn't it? Good. All right. The second handout that I gave you today talks about electron level diagrams. An electron level diagram just provides for us information about transitions that can take place within an atom. This particular electron level diagram is for hydrogen. All electron level diagrams for every different element would look similar, but they would have different numbers. Okay, what do you notice about the basic structure of this diagram? First of all, we call this the ground state, so the nucleus would be down here. The ground state would be the first level. Then, of course, we have excited states. Okay, so when an electron has jumped from the first level to a second level or a third level, it's in an excited state. Notice the spacing between the ground state and the excited states. The further we get away from the nucleus, the closer these levels get together. The smaller the difference in energy becomes. Now, these numbers are different for every different element again, but the same basic structure holds. The difference between level 1 and level 2 for hydrogen is about 10 electron volts. But between level 2 and level 3, it's only about 2 electron volts. They keep getting closer and closer together as you go further away from the nucleus in terms of spacing, but also in terms of energy. The numbers will be different for every element that you see. And you could see a diagram like this for any element, but the structure of it should be the same. Whenever you see a diagram for another element, it should look the same. It should remind you of this. Now, what do these lines correspond to here? All these lines correspond to possible transitions that can take place from high levels to low levels. So we could get an electron transitioning from level 2 to level 1, or from level 6 to level 2, or from level 5 to level 1, so on and so on and so on. Each of those sets of transitions has names associated with them, although you don't need to remember those names. Okay? That's just for perspective here. Now, of course, these electrons can make the opposite transitions as well. When this happens, they give off energy. Right? From level 2 to level 1, it gives off a photon. From level 5 to level 1, it gives off a photon. From level 6 to level 2, it gives off a different photon. But the electrons can also jump from level 1 to 2, from level 1 to 5, or from level 2 to level 6. In that case, it's the exact same photon, except it's absorbed instead of given off. Make sense? We're going to do a couple of calculations with these electron level diagrams, but listen carefully to what I'm about to say. Okay, these questions that you see are not hard at all. But there's one error that is relatively common. Whenever you're doing calculations with these diagrams, you always want a difference in energy between two levels. You never want the energy of a particular level. Never. So for instance, if you're dealing with the third level and the fourth level, you never want level 3 or level 4. You want the difference in energy between level 3 and level 4. Does that make sense? Anytime you need an energy from this, take the difference in energy between two levels. One more thing before we do an example, actually. Notice that these are negative values, negative energy values. That's a little bit odd, hey? Why are they negative? Starts at 0, where the electron is at the infinite level, where it's a free electron. Right, it's left the atom, right? The electron has gone to the point where it's not orbiting the nucleus anymore. It's free. The energy is 0 at that point. But we say the energy as we go down towards the nucleus becomes negative. Right now, you're sitting on the surface of the Earth. What would you say your gravitational potential energy is right now? Depends on what it's relative to, right? You said 0, but it depends on what it's relative to. Relative to the surface of the Earth, it's 0. Relative to the core of the Earth, it's not 0. We're going to define it relative to the surface of the Earth because that's what we usually do in the context of gravitational potential energy, right? What happens if it's 0 right now? What happens if you dig a deep hole, put a ladder in that hole, and start climbing down the ladder? Your gravitational potential energy relative to the surface becomes negative, right? So that's what this is here, right? The potential energy of these electrons on various levels become negative, become more negative the deeper you go into the Earth, right? This would be the surface of the Earth, where we've left the Earth. But as we go down into the Earth, or as the electrons go down into the atom, start orbiting the atom, inside the atom, and as they get closer to the center of the atom, which is the nucleus, their potential energy becomes negative, and it becomes larger values of negative. All right? Let's do a little question here. And this one's on the handout, I think. Yeah, I think they all are, actually. Using the above diagram, determine how much energy is emitted in the second line of the Balmer series in the hydrogen atom. The second line of the Balmer series. Now, again, you don't need to memorize what the Balmer series is. Yeah, you have it labeled on your diagram here. But the second line of that Balmer series would be this one. So we want to find the energy that's released in the second line of the Balmer series. Remember what I said a minute ago? I said, pay attention to this. Okay, this would be the most common mistake that people make with this. You always want to use not this number or this number, but the difference between those two numbers. So let's do this. The difference in energy between those two numbers is negative 3.4 electron volts, subtract negative 0.85 electron volts. You don't forget to subtract the negative. So the difference in energy is negative 2.55 electron volts. Technically, the energy released would be 2.55 electron volts. We wouldn't say negative, but we're not going to run into an issue where that's a problem. So we release 2.55 electron volts of energy. Easy enough? Okay, I got a question for you. What if we wanted to find the frequency of EMR that was released here? Because remember, EMR was released when we went from level 4 to level 2. We got the energy of that transition, the energy of that photon that was released. How do you find the frequency of that photon that was released? I'll give you a hint. It's easy. It's easy. Joseph? Yeah, you just found the energy that was released by that transition. It's a photon. So all you do is say 2.55 electron volts equals, we'd have to use the 4.14 value because we're in electron volts here times the frequency. You could do virtually the same thing for wavelength, right? If you wanted to find the wavelength released, you could say the energy of the transition, not the energy of the fourth or the second, but the energy of the transition, the difference that we just found, is equal to hc over lambda and solve for lambda. Okay. How about this one? What's the ionization energy for an electron on the first level of hydrogen? In other words, how much energy does it take to cause this electron to leave the atom? There's our diagram. On the first level, we have negative 13.6. What do we got on the infinite level when it's left the atom? 0. How do I find the energy that's required to go from here to here? Subtract again. Do the same thing. Except this time, we're going from level 1 to level infinite. We're going to say 0 minus negative 13.6. So the ionization energy would simply be 13.6. You could figure out what frequency of light was required to do that. What wavelength was required to do that. All right? Not so bad, right? Stuff isn't so bad. You know what? We won't even bother doing this one. I think we're okay with this stuff. This is the same thing, isn't it? It's just another repeat of the same thing we've just done for the last two questions. Okay, the only thing that these three questions haven't asked, we addressed it right here, but the questions themselves never asked you to find frequency or wavelength. That's a relatively common thing to be asked, not just to find the energy of the transition, but the frequency of the photon that's emitted or absorbed as well. One more little thing, one final little thing with this. Let's say that some source of energy, photon, some other source of energy, whatever, some source of energy that was, let's say, 11 electron volts was absorbed by an electron on the first level. What would happen? What could, I should say, what could happen to that electron if 11 electron volts was absorbed? Could it get to the second level? Could it? How much does it need to get to the second level? 10.2, right? We'd say negative 3.4 minus negative 13.6, it would be 10.2. Could it get to the second level? Yes, because 11 is more than 10.2. Could it get to the third level? No. So if this energy was absorbed, actually not all of it would be absorbed. 10.2 of this 11 could be absorbed, causing the electron to jump to the second level, but you can never get to the third level with this amount of energy. Make sense? So you need at least, what would it be to get to the third level? About 12.05, I think, 12 point something to get to this, to get to the third level. Okay. We just finished talking about the Bohr model of the atom now. Dalton solid sphere, Thompson plum pudding, Rutherford planetary model of the atom, Bohr model of the atom, right, which electron levels. We're going to finish off today by talking about the last model of the atom, and this is the currently understood model of the atom. This is the one we currently buy into, even though it's almost 100 years old, 84 years old, 1930, I think it was. The Schrödinger, the quantum mechanical, the electron cloud model of the atom. All of these things mean the same thing, so be prepared to see any of those terms. Schrödinger, quantum mechanical, electron cloud model of the atom. What this says is, you know what, it's a step forward, but in a sense it's a step back. The idea is that we have a small, dense, positively charged nucleus, and now by this time we know about protons and neutrons inside that nucleus. And the electrons orbit around that nucleus, and they orbit on levels, but it's kind of weird because we don't know exactly where those levels are according to this model. So isn't that kind of going back kind of in between the Rutherford model and the Bohr model? No, not exactly. It's not saying that it's random, the position of these electrons. We're saying that it's a quantum mechanical phenomenon, which means that we can't know. It's an acknowledgement, not that we don't know where these electrons are, it's an acknowledgement that we can't know where these electrons are. These electrons, what this model says, exist in clouds surrounding it. They're on levels, but those levels are within clouds. There's a certain probability that we'll find an electron right here. There's another probability that we'll find an electron right here. Another one that we'll find an electron right here. But we don't know for certain until we've found it. It's kind of like radioactivity, right? We don't know for certain when things are going to decay until they've already happened. Make sense? Now, Bohr predicted exactly where these electrons would be found, right? Now we're saying, well, those predictions aren't exactly right. The most probable location to find the electron would be on the Bohr radius, where Bohr calculated it to be. So Bohr's not all wrong. The most probable place that we'll find it is there. But we don't know for certain because there's a somewhat smaller probability that we'll find it in some other place. You know what? I'll give you an analogy here. Answer this question for me, please. Where's Mrs. Stafachuk right now? Where is Mrs. Stafachuk right now? The most probable location for Mrs. Stafachuk is where? In her office, right? In her office. That's where Bohr predicts she is, in her office. And that's the most probable location that she'll be found. But there is a real possibility, although a smaller probability of it, that she's teaching a class down in the math wing. There is a real probability, albeit a smaller one, that she's outside doing something. There is a real probability, albeit an even smaller probability, that she's left the building somewhere and is in her car in Okotoks running an errand. There's an even smaller but real probability that she's in Calgary somewhere doing the same thing. There's an even smaller but real probability that she just got tired of this cold and hopped on an airplane this morning and went to Mexico. Do you see what I'm saying here? These electrons, we're going to predict that they're at the Bohr radius, and that's the most probable location, but there is a real probability that they could be somewhere else. In fact, the electrons orbiting around this nucleus that's right there, that I'm pointing at right now, the electron could be in Calgary, although it's an incredibly small chance that it could be there. Right? Its most probable location is that Bohr radius, which is really, really close to the nucleus. Make sense? So step forward, but step back, kind of at the same time, if that makes sense.